Welcome to the fifth lecture of EE298, Generalized Principal Component Analysis. So to start this lecture, let's first review what we have discussed last time. So last time, Professor Sastry gave a more rigorous definition of the problem we are going to solve, Generalized Principal Component Analysis, and also showed a procedure to solve a special scenario when you want to segment multiple hyperplanes. Let's just review this process a little bit. And suppose you have, for a very special example, suppose in R2, you have 3 lines on a plane. And what's the first step you're going to do? So you have 3 lines on a plane. S1, S2, S3. The first thing you're going to say is that each one will have a normal vector, right? So each subspace is defined by its normal, B1, B2, and B3. And then you said that any sample that is from the union of S1, S2, and S3 must satisfy a single vanishing polynomial, P3 of x, which is equal to the product of 3 terms, 3 linear terms, B1 transpose x times x, and B2 transpose times x, and B3 transpose times x has to be equal to 0, right? And next, you are going to take the derivative of this vanishing polynomial, and you are going to get 3 terms like the following. And if you happen to also have samples from S1, S2, S3, you only need 1 sample per subspace, and you evaluate the derivative at those points. And for example, if you evaluate the derivative from a point from the first subspace, you can see that because if x is from, so if, I need to switch to another one. So we said that if x is from S1, we know that B1 transpose x has to be equal to 0, right? That eliminates the third term, the second term and the third term of this equation. And so you get, so the evaluation, the derivative of P3 of x evaluated at this position, particular position, I rename it S1, is equal to only the first term, that is B2 transpose x, B3 transpose x times B1. Right? But this is a scalar anyway. So you only need to know the orientation of the normal vector that's perpendicular to S1. So which tells you that P3 of x evaluated at x1 so is equal to a scalar coefficient times V1. I don't care about this scalar as long as it is not 0, because I know that this guy, which means it's perpendicular to S1. I can use this relationship to already partition to find all the samples in the mixture that belongs to S1, right? Any point that is orthogonal to that normal vector I can find. So in general, if you have capital K number of hyperplanes, so you can still use the same strategy to find the corresponding unique vanishing polynomial, at least up to a scale. And you can take the derivative of that vanishing polynomial, and because of this relationship that you evaluate the derivative of the vanishing polynomial at 1 point per subspace is going to eliminate all the terms except the term that is a scalar difference of the normal vector of that hyperplane. Okay? So the last thing you are going to do if you want to find a orthonormal basis. So it's to normalize the length of the derivative, and then you get the normal vector for hj. Right? So that's the strategy we have talked about last time for hyperplanes. Are there any questions? So here is the algorithm 3.3 as a summary of the algorithm, algebraic hyperplane segmentation algorithm. And we have just used the example to talk about the process of finding normal vectors. And after we find a normal vector, we use the relationship of orthogonal of the normal vector always orthogonal to the subspace, and then we can do the segmentation of the sample points. And can anybody remember how do we find the number of hyperplanes? The number of hyperplanes is to use Verneza embedding, and then you can try the Verneza embedding of order 1, 2, 3, 4, 5, and then you keep raising the order. And the number of the optimal number of group is the minimum value that is the first value, the smallest value you see a rank 1 deficiency in terms of the embedded data matrix. When the data matrix drops ranks, and by 1 in this case, because it is hyperplane case. So this is the smallest number that satisfy this condition. That also give you the number of the hyperplanes. Okay. So today we are going to talk about the segmentation problem under more general condition. That is how to segment the general subspace arrangement. First, we are going to give some extra condition that we assume that we are going to know the number of subspaces. And later on, we are going to consider a more general condition that given the strategy we have for the first problem, how to, in addition, recover the number of subspaces and their dimensions. Okay? So that's what we are going to talk about today. So again, let's start with a simple example. So in this example in R3, let's suppose we have two subspaces. The first one, S1, is the line, okay, which can be defined by two normal vectors, S1 equal to 0 and X2 equal to 0. Right? And the second subspace is a plane. In this case, it has a single normal vector, which gives you S3 equal to 0. Okay? And we know that if we pick an arbitrary point from the union of the two subspaces, it has to satisfy the following constraint. That's exactly the same as what we did for hyperplanes. That is, this point, if x is from S1, it has to satisfy this constraint, the S1 equal to 0 and X2 equal to 0. Okay? And if S2 is, if X is from the second subspace, it has to satisfy the second constraint, that is X3 equal to 0. And then we use De Morgan's rule to swap N and Os in this constraint. And then we end up with two second-degree vanishing polynomial. That is X1, X3 equal to 0, and X2, X3 equal to 0. Can anybody understand this? So this is X1 equal to 0 and X2 equal to 0, or X3 equal to 0, and then you swap N and Os, so you end up with two vanishing polynomials of degree 2. Okay? So how to find the two vanishing polynomials of degree 2? In this case, we again use the Verneza embedding. So in R3, the Verneza embedding will give you C1 of x1 squared plus C2 of x1, x2 plus C3 of x1, x3 plus C4 of x2 squared plus C5 x2, x3 plus C6 x3 squared. Okay? So that is one Verneza embedding of order 2. And suppose you have n samples. So you are going to construct a data matrix, embedded data matrix, that consists of Veronese embedding of x1. So those are vectors now. The second sample, da da da. And I said that this data matrix is rank deficient. What's the rank of the null space? What's the dimension of the null space of V2? Hmm? Two. In this case, it's still easy because we have two vanishing polynomials. We got to get those coefficients from the null space of the vanishing polynomial. Because we know that previously we know that this guy, because we know we have two vanishing polynomials, P1 of x equal to x1, x3 equal to 0 for any points from the union of S1 union S2. And we know that P2 of x equal to x2, x3 equal to 0, right? The same condition. So I can tell you that if you give me this data matrix, I can easily find two basis vectors. That's when you do the multiplication of the vector times this matrix is going to give you 0, which gives you the definition of null space. So let's track this down. So this one is x1, x3. So the first vector I'm going to use is 0, 0, 1, 0, 0, 0 times v2 equal to 0. Right? You look at this guy. No matter how the other terms change, because this term is always 0. I put a both eye in here. Because no matter which sample you are going to use, so this row is going to be always 0, right? So which means you set all the rows to 0. You use this to eliminate all the rows, but you set this one to 1 because the corresponding row is 0, so this one equal to 0. Okay? And then there's another one. So this guy is also always equal to 0. So I have another vector. This is always equal to 0, right? And they are linearly independent. So that gives you that the dimension of the null space of V2 is equal to 2. Okay? So after you use that, so numerically you evaluate the Veronese embedding, and then you compute a basis to represent the null space from the coefficient. You can get back, you can find these two polynomials. After you get hold of this polynomial, you take a symbolic derivative of that, so you get this matrix. Okay? If you care to check, so P1, P2, that gives you the derivative of, this is the derivative of x1, x3. So x1, x3 derivative with respect to x1 is x3, with respect to x3 is x1. So this is the derivative. This column is the derivative of x2, x3. Okay. Now the same strategy, and you evaluate this derivative at any representative point for 1 point per subspace. So to play a simple game, so let's suppose I write down one sample from S1. Remember, that's a line. Okay. So the line, I'm going to choose the coordinate 0, 0, 1. In this case, the evaluation of the derivative of P is equal to 1, 0, 0, 0, 1, 0. Okay. So what is this? What are these two vectors? I think that by now you can almost guess without any computation that this exactly gives you the two normal vectors perpendicular to S1. It's the same. And you do the evaluation of the second one, that gives you single normal vector perpendicular to S2. Okay? So the conclusion is that after you evaluate the derivative, if you compute the rank of this guy tell you the codimension of Si. Remember, the codimension is d minus the dimension, okay? Which is also the dimension of the subspace that's orthogonal to the subspace. Okay. Yes?
Is the P subscript Xi just a way of notating the gradient?
P? Capital P? Capital P is just the list of the vanishing polynomials. Yeah.
But the sub Xi. Right.
So just take the derivative of P, capital P is just taking the derivative inside the list. So it's with respect to taking the derivative of P1, taking the derivative of P2, so you have two columns in here. Okay. But on the other hand, you see when you compute the rank of the second matrix, because the codimension of S2, which is a plane, is what? It's 1. So even you have two columns in the original P matrix, the derivative of P, when you evaluate that at a point from S2, you only get rank 1 matrix. So you get two identical normal vectors that are both perpendicular to S2. Okay? Oh yeah, should be S1. Yeah. Yeah. So that's a typo. Yeah, that's a typo. Okay, I see. Big typo there. All right. So the remaining question is, a lot of promises has been made, but still, how to choose one representative point per subspace? Okay. In the noise-free case, it's easy, right? So because noise-free case, as long as you don't fall into the origin, and then the normal vectors you are going to estimate are going to be always perfect. So they are always perpendicular to the subspaces. So you can just randomly pick one. And if you really want to be sure that you don't pick the intersection, what I mean by that is that consider another case that if you have two subspaces, so you also want to avoid evaluating the derivatives at the intersection of the subspaces, because the orientation of the normal vectors at that location can be arbitrary, right? So if the data are perfect, you can randomly choose some of them, and then you can see where are the consensus. So you just find the highest consensus for the direction of the normal vectors, and then boom, that's your solution. But however, in the noisy case, what we want to do is that we do have this P. We do have still have this list of vanishing polynomials. So what we want to do is to choose one that's really close to the zero set that is represented by the vanishing polynomial. Okay? So we want the point to be close. So in this example, suppose we have some points that are right on the zero set of the vanishing polynomial, but we also have some points that are quite far away due to the noise. We are not talking about outliers yet. So what we really want to do is to find the points that are really close to the zero set. Okay? So you're going to see later in the lecture what we are going to do is to, with respect to all the points, we are going to try to project this point, all the points onto its closest subspace. And then we are going to find the one that has the smallest distance of the projection. Yes? The motivation previously, I said that if you can pick one point per subspace, I can give you the orientation. I can give you the orientation of the normal vectors. But you still have to tell me where are those points. Because you have a whole bunch of points. You have n samples. Right? So we start with n samples. But if we only have k subspaces, out of n samples, we need to pick k representative points to evaluate that derivative of P. So that's the motivation.
So at this point, like in the algorithm, we figured out how many subspaces there are?
Capital K.
And we have a means of determining
in the first,
what they are if we can just pick a point that's in each one.
Well, in that case, you know the coordinate of the samples, but you don't know the location of the subspaces, right? So that's the whole idea of subspace segmentation. You do have all the samples. And from the samples, you take the Veronese embedding. In fact, let me see if I can. Yeah, here it is. Perfect. So let me just use this one to summarize. So if you, feel that you feel lost along certain steps. So we start with a whole bunch of points. Remember, we don't have this structure. We don't have the structure of subspace. Just imagine that you only have those points. Now, for the first part of this lecture, I told you that I assume that I know the number of subspaces to be 2. So I'm going to take the Veronese embedding of order 2, and I map those samples into a higher dimensional polynomial space. And then this mapping is going to be degenerate, right? Because the null space of the mapping gives me the coefficient for vanishing polynomials. Right? After I get hold of vanishing, so remember, when I find the vanishing polynomials, those vanishing polynomials are found based on the mapping of all the samples. Right? Based on the null space of this data matrix, this data matrix has columns of all the samples. Now, after this point, I have to reduce the problem to evaluate the derivative of this P for only one sample per subspace. So the answer to your question is that from n samples at the very last stage, I only need to evaluate the derivative of P at 1 point per subspace. So is that clear enough?
I think so.
Okay. So this, in fact, this is the image you want to you remember if anybody asks you, outside the classroom. So what did you learn in the GPCA? So what's the general definition and process of GPCA? The easiest way, within 1 minute is to just draw this figure, and then immediately you can explain what's the problem definition and what are the 3 key steps. Okay. So we are going to follow this. Today we are going to follow this diagram to investigate more in more general conditions how to implement the exact 3 steps. So the conclusion before we move on to remember is that so in this case, at least from the toy example, that using vanishing polynomials, we seem to be able to convert, using GPCA, a previously chicken and egg problem into a closed form solution. Right? Previously, we said that you start with a whole bunch of points. You don't know the membership of the points, either from the line or from the plane. You also don't know the parameters of the subspaces. So it seems to be a chicken and egg problem. If you know the membership, solving for the parameters of the subspaces become extremely simple, just using PCA applied to each individual group. And if you know the parameters of the subspaces, you just based on the nearest neighbor, you can project the samples onto the subspaces. But in this case, we introduce a new process that in the middle, we plug into a Veronese embedding, and from the null space of Veronese embedding, we recover the vanishing polynomials. And from the 0 set of the vanishing polynomials, we recover the normal vectors. Okay? So that's the key point of GPCA. If you want to remember one single slide in this entire course, this is the slides for you. Okay, so next we are going to go one step further from special cases to general cases. So remember, the first step is from a whole bunch of points, how to fit polynomials. So the first observation is that in general, when the dimension of subspaces are mixed, so in this case, you don't have all hyperplanes. You can have subspaces of dimension 1, 2, 3, 4, 5. In this case, actually, the set of kth degree vanishing polynomials become more complicated. Finding those vanishing polynomials become more complicated. We have just seen one example, right? So if we have just one plane and one line, the number of vanishing polynomials will be 2, right? It's not going to be 1 anymore. So which means the dimension of the null space is 2. In fact, you can consider more complicated situation. To show you an example, I put an example in this slide. In this case, in R3, so I'm going to consider all the different combinations, at least non-trivial combinations, which means I'm not going to consider subspaces of 0 dimension. Our subspace of 0 dimension means just origin, right? So if I eliminate the trivial case, I'm going to have, with respect to, if I know I have 3 subspaces in R3, all the possible combinations for subspaces are 2, 2, 2, 2, 2, 1, 2, 1, 1, and 1, 1, 1. Okay? So the left-hand side of this table shows you all the combinations. the right-hand side actually show you, if you do some simulation, you can generate samples, noise-free samples, and then you can take the Veronese embedding in MATLAB, you can compute, you can verify the null space of the embedding. So those are the corresponding dimension of the null spaces, 1, 2, 3, and 7. Okay? So let's do a little bit exercise to help us to appreciate where are the problems. Okay? So, well, for the first case, is the first one easy or hard? In R3, so in the case if D1, D2, D3 combination is equal to 2, 2, 2, what do we get? Hyperplane case, right? So in that case, we know that we are going to have one single normal vector perpendicular to S1 and another 2, 1 perpendicular to S2, and we are going to have B3, 1 perpendicular to S3. In this case, the next conclusion naturally will be there exists a unique vanishing polynomial up to scale that P of x equal to 0. What is P of x? It's equal to B11 transpose x times B21 transpose x times B31 transpose x, right? We know this case already. How about the second case? The second case is also very similar to the toy example. So in the toy example, we have 2, 1. In this case, we have 2, 2, 1. But it's a similar case. So let's consider if the combination is 2, 2, 1, then we have B11 transpose, B11 is orthogonal to S1. B21 is orthogonal to S2, perpendicular to S2. And for S3, because it's one-dimensional subspace, we have two normal vectors, right? So we have B31 perpendicular to S3 and B32 perpendicular to S3. Correct? So in that case, we have two vanishing polynomials. And they are B11 transpose x times B21 transpose x times B31 transpose x equal to 0, and B11 transpose x times B21 transpose x times B32 transpose x equal to 0. Okay? And you can continue. So if the combination is 2, 1, 1, how many vanishing polynomials do we have? Can anybody take a wild guess? 4, right? So you can see from the table. So why is 4? Because now let me stick to the same notation. I have S11, B of x11 orthogonal to S1. Now I have a pair, B21, B22 orthogonal to S2. And I have B31, B32 orthogonal to S3. Okay? And then you do all the combination. You go this route, you go this route, and then you go this route, and then you go this route. And then you end up with P1, P2, P3, and P4. Okay? Now, how about the last situation? The last one, the combination, if the combination is 1, 1, 1, then we have B11 perpendicular to S1, B12 perpendicular to S1, and we have B21 perpendicular to S2, B22 perpendicular to S2, we have B31 perpendicular to S3, and B32 perpendicular to S3. You know, by doing this procedure, how many polynomials do you have at the end? 2 times 2 times 2 equals 8, right? But why, on the right-hand side, we only have 7? So now you know why I go through this process. is to raise the question, why this is 7? Why this is not 8? Can anybody take a guess? When you have more and more polynomials, eventually you're going to have some situation that is different from smaller number of polynomials. The answer is, when you have more and more polynomials, they may become dependent, right? So on the surface, you may have more and more polynomials, but at the end, when you compute the rank, some of the polynomial can be linearly expressed as a combination of some other polynomials. Then you don't have rank A, you have rank 7. To give you an example, suppose I have P1 equal to x1, x3. Now, if I have P2 equal to x2, x3. Now, hypothetically, if I happen to find another polynomial P3 is equal to x1, x3 plus x2, x3. Now, if this guy vanish on the union of the subspaces, and this guy also vanish, how about this guy? This guy also vanish, right? So by doing that, you can find this guy. It is possible that you can find this guy. But however, because this guy is a linear combination of P1 and P2, if you put those guys together and then you compute the rank, at least for the corresponding for the corresponding embedded data matrix, the corresponding coefficients. So that corresponds to the coefficient. Remember, I wrote the coefficient with respect to B2. So what's the corresponding coefficient for this one? Is 0, 0, 1, 0, 0, 0, right? The coefficient for this one is 0, 0, 0, 0, 1, 0. What's the coefficient of this one? The coefficient of this one is 0, 0, 1, 0, 1, 0. But this one doesn't give you an extra dimension for the null space, because this one is within the subspace spanned by the first two. So that's the reason. Okay? So that brings to the very important slides for this of this slide. So is that so let's try to investigate this this situation in a more general term. So in general, we can define a vector space for the polynomials. Homogeneous polynomials of the same degree. So the first one is that given a fixed ambient space, Rd, and all the polynomials of degree k, in fact, give you a vector space. So we are talking about linear dependency, linear independence, so we are talking about that with respect to a vector space. So let's denote that as ik of 0. So it will be clear in a minute why I wrote 0 in this case. So, for example, when d equal to 3 and k equal to 2, we already know that any homogeneous polynomial of degree 2 can be written as c1 x1 squared plus c2 x1 x2 plus c3 s1 x3 plus c4 s2 squared plus c5 x2 x3 plus c6 s3 squared, right? Any polynomial can be written as this form. And what's the dimension of this vector space in this case? The dimension of, let's say, k of 0 is equal to what? What's the dimension? How many degree of freedom you can change in this equation? 6. You can vary in total 6 number of scalars. So the dimension is 6. And can you give me a basis for this vector space? Or for this polynomial space? For this vector space contains polynomials, homogeneous polynomials. All the hints are already on the whiteboard. Each of the monomials, good. So the basis is just x1 squared, x1, x2, x1, x3, and x2 squared, x2, x3, and x3 squared. So that actually is the exact list of Veronese embedding it will give you. Now you see why we use Veronese embedding. Because you are going to raise you use the point to raise your sample points to a certain vector space that contains polynomials, homogeneous polynomials. And they form a vector space. Okay? And after the embedding, you are going to reduce. So you're not going to. So it is not true that all the homogeneous polynomial in this vector space is going to be give you the union of the subspaces, right? The vanishing polynomials, that's the second point. In fact, the case degree vanishing polynomials form a subspace of this vector space. So which means Ik of the zero set of the subspace arrangement actually becomes a subspace of this vector space. Okay? That's the second point. Is a subspace. So why this is a subspace? Because as we have just shown that many times that any vanishing polynomials of degree 2 of degree k is a linear combination of all the monomials, right? So from the basis, you can form any elements in this set, okay? And also, if P1 is from this set, which means P1 of x equal to 0, okay? And if P2 is the same, what do we have? Any linear combination of P1 and P2 also equal to 0, right? So if you define any P3, P bar, P prime equal to alpha 1 P1 plus alpha 2 P2, and P prime evaluated on all the points from the union of S1, from the union of K subspaces is also equal to 0. Okay? Second condition, it is a subspace. And the third condition, you have to check 0 is in there, right? The 0 polynomial you evaluate at any point is going to give you 0. So this subspace also have a 0. So this indeed is a subspace. The next one, the next result is that now the definition for the dimension of this one is interesting. Okay, so it's in fact that the dimension of the subspace that forms the set of vanishing polynomials is called the Hilbert function of order k. So in here, in algebraic geometry, it's denoted as hi of k, of degree k. Okay. So by now, you may think that, well, this looks like a very classical solution, right? You know, Hilbert has actually asked that if you are going to grade all the polynomials that is going to vanish on certain algebraic set, which means you are going to write down the subspaces with respect to all the kth degree polynomials, and you also k plus 1 degree, right? Because any polynomial that vanish on a algebraic set, you multiply by x, it's still equal to 0. So once you have k, you can naturally get k plus 1, k plus 2, k plus 3. So it becomes a graded series of infinite many polynomials. So that actually question was raised by Hilbert in his 16th problem. But it turns out that this is rather a very difficult problem to solve. So actually, when we started the GPCA problem, I believe that we were one of the first groups that posed some of the conjectures based on our simulation. That is exactly what we did when I show you the tables. Based on the table, you can derive some conjectures for the closed form solution. And then finally, this closed form solution was proved by Dirksen in 2005. So you can see that this is a fairly new result, so which tells you that the underlying method and the underlying problem is much deeper than we originally thought. So it's not an easy problem to solve. So to explain this equation a little bit, so this S actually is a index set from index 1 to k, including empty sets. Okay? So C of S is the summation of the codimension of the corresponding subspaces. Okay? So if you have 1 to k subspaces, so you are going to exhaust all the linear combination of picking those subsets of this index set. And then after you pick the indexes, and then correspondingly, if you also know the dimensions, you can compute the sum of the codimension, and then you put that one into the equation, and then you get, basically you get a table, with arbitrary combination of subspaces. Okay? So finally, the conclusion you need to remember is that with this result, that thanks to Dirksen, then we can show that if you know the number of subspaces, also you know their dimensions, and then you can exactly compute how many vanishing polynomials you are going to have, at least linearly independent. Okay? That's the explanation in the first table I showed you why the last row, the right-hand side is 7. Because this equation tells you 7. And from the simulation, when you raise the samples to the third order with respect to 3 subspaces, the dimension of the null space from numerical result also verifies is 7. It's not 8. Okay? So that's the conclusion you want to remember. Okay? So that's the last conclusion. The dimension of the null space of the embedded data matrix is equal to the dimension of the polynomial subspace that contains all the vanishing polynomials of your subspace arrangement. This is exact definition of the Hilbert function of case order. Okay? Are there any questions? This is probably one of the most important results of this lecture. If you want to remember easily, you can just remember that table. 1, 2, 3 is simple. From hyperplanes to a intermediate level difficulty in the arrangements, and at the end, eventually you are going to reach some point that some of the polynomial you find from the linear combination of all the normal vectors going to be linearly dependent. So that actually brings you to that equation. Okay. So the conclusion is that with the closed form solution, even when the sample data are noisy, as long as you know k and their dimensions, you can just look at the checkout table, and then you can use PCA to feed the best null space from your data matrix. And then you can use that polynomial. You can use the coefficient of the null space to give you the best estimate for the vanishing polynomials. And then you can use that to do segmentation. Is that clear enough? So which means what I'm saying is that in the noisy case, V3, let's stick to the example of that table. So you raise the order of Vernet embedding to the third order. You have x1 V3 as n. Okay. So if this is noisy, this guy is going to be full rank, right? So if you compute the singular value decomposition, you are not going to see any 0 value in the singular value. But what I'm saying is that, so suppose you do SVD of V3 is equal to USV. Okay? So what you can do is that, so you look at the diagonal of S. of S equal to S1 da 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 of let's say Sm. So in that case, if you know from the lookup table, you know that if there's no noise, what's the dimension for the null space, right? So you can manually set the last singular values, even they are not 0, to 0. The corresponding vectors in singular value decomposition will give you the coefficient for the vanishing polynomials. Okay, that's what I meant. So the second step, so we just walk one step forward. So that if you remember, the second step is after we get hold of the vanishing polynomials, we just take symbolic derivative of that. So that actually is very easy to implement. Certainly it's not hard, but it takes some time to really write a generic solver in MATLAB to track down the rules when you take derivatives. Basically, the simple derivatives of polynomials. Okay, if it is nth order, you move n in front as a scalar, and then you put the order to n minus 1. So those rules you have to implement that in MATLAB. But in any case, you can take the symbolic derivative of polynomials, and then you can get the derivative, the expression for the derivative of polynomials. Okay, there's no secret for that. So you just need to implement that either in MATLAB or Mathematica. In Mathematica, probably it's easier because you can do that symbolically. So now we circle back to the very last question we didn't answer. At least we answered only loosely. Is that in general, how do you choose one sample per subspace? After we assume all the way that from the noisy points, we know the null space of the Voronezh embedding, we can get P. From P, we can get derivative of P. Now we go back to the last question we didn't answer. Is that given n samples from k subspaces, how to choose one point per subspace to evaluate orthonormal basis? Yes?
In the noisy case, that seems really counterintuitive to me, that you would just choose one point at which to estimate your normal vectors. It seems to me that you use your data and to have some sort of estimator.
Okay. So the question was that in the noisy case, it seems that we shouldn't trust any sample because any sample could be noisy. And because also the coefficient of the polynomial are estimated from noisy samples, so we shouldn't trust any simple sample. We should somehow find a consensus of all the samples. So, which is a good point, actually. We have an exact version for that in our website, in the GPCA website. If you go to the GPCA website, so that's exactly the strategy we do. But it's a little messy, so we didn't mention that in the book, or probably later in the book. So it's called GPCA voting. So that actually implements exactly the idea that you have. Is that if you have noisy samples like this, so one point is going to give you this, another point is going to give you that, another point is going to give you that, right? So what you can do is that you can evaluate all the points, and then you can take the average. You can compute the angle. You can compute the mean of the angular difference of those samples. Eventually, the average of the entire sample will give you the normal vector.
Well, some of the data points also, in terms of membership in noisy case, it seems like some points you'd have a higher confidence in the membership as opposed to other points. So you're talking about a weighted average?
Weighted average, yes. So in that case, actually, you're not going to choose one point per subspace. For each point, this point could come from this one or come from this one. So you have to have the assumption that if this point comes from S1, S2, you're going to retain the first leading two orientations. If this guy from this one, you have to assume that you're going to retain the first one. But you can see that only when the membership of the right sample is enforced, you're going to get consistent estimation, at least they're close. If you are going to estimate a single normal vector, so you're going to have a lot of like this, right? But at least they are close. But if you are going to try to find a leading normal vector direction perpendicular to S1 from here, it's going to be possibly all over the place. So you're not going to get a consensus. So eventually, after you evaluate all the possibilities, you are going to see a high consensus of all the points that give you roughly the same direction along this direction. And all the samples on this plane, in this case, you cannot compute the direction anymore because any rotation of those subspaces, any rotation of those normal vectors is still a valid subspace perpendicular to S1. So you compute the subspace angle. You compute the subspace angle of those points. You're going to see a consensus of the subspace angle that is indeed perpendicular to S1. So that actually is the gist of the voting scheme. So if you use voting, you are going to bypass all these techniques that we are going to discuss. But let's stick to the book because I think that what we have in the book has some important message we also want to remember that actually applies to any arbitrary algebraic set. So eventually, in the future, if you see other type of algebraic set, hopefully you can also learn from this how to do projection to the algebraic set, to the zero set of a algebraic a zero set defined by a set of algebraic functions. So what we are looking for the optimality is to choose best sample. Okay, so this is the question actually. The question is, what's the notion of optimality in choosing the best sample when the set of vanishing polynomials are given? Okay. So let's again start with a simple case that everybody probably can work with. So let me give you a set of hyperplanes. Can you derive a single strategy to give me 1 point per subspace? They are all hyperplanes. Give me one sentence solution. No taking derivative. You know the algebraic set, which means you know the algebraic you know the polynomials that define the zero set. You know P. Remember our several steps. We start with sample points, whole bunch of points, and then we go one step further. We have Veronese embedding, okay, and then we have this V matrix. From V matrix, the V matrix is rank deficient, and then we take one step further. We have the coefficient from the null space, okay. From the coefficient of the null space, that give me the subspace structure in the polynomial space, okay? And that give me the P, capital P, equal to a whole bunch of small p's. From there, if I happen to know that the case is hyperplanes, it means I only have one P, right? Because it's rank deficient by 1. The embedding, the Veronese embedding is only rank deficient by 1. Is there any easy way that you can find to give me one sample per subspace? Okay. The answer is simple. You randomly draw a line. As long as the line doesn't pass the origin, that is going to give you k points. Two subspaces. 2 planes in R3, you randomly draw a line. That gives you 2 points. As long as this one doesn't pass the origin. So how do we do? Suppose this line is parameterized. You can randomly choose V and X not. That's what I mean by random. You randomly choose the orientation. You also randomly choose the affine term, X naught. And then this line is parameterized by a scalar coefficient, T, along this line, right? And you know that when this line intersects with the algebraic set, that's the zero set of the polynomial, you know that this pk is going to be equal to 0. Remember, we only have one pk. Okay? So that helps a lot. So at the end, so the problem is reduced to finding k roots in this vanishing polynomial. That's it. After you get the roots, you put the solution for t from t1 to tk back to the line equation, and then you get the k points. That's simple enough. Okay. So that's the hyperplane case. Also, preferably you don't have that much of noise. So in the general case, this is the case in Lemma 3.9. it says we should choose samples as close to the 0 set defined by the algebraic functions as possible. Okay? So in particular, so the warning shot is that one should not choose points based on px. So what you don't want to do, a big no-no, is that after you get hold of p of x, you don't want to find those points that give you the value of p of x close to 0. You don't want to do that. Not good. Why? Because that only tells you the algebraic error when you evaluate that on the polynomials, but not the geometric distance. What you want to find is the distance from x to x tilde. So this x tilde sits right on the algebraic set. What you really want to find is this guy. But p of x doesn't tell you this measure. Okay? And there's another reason why you don't want to choose p of x to be extremely small, is that actually on the opposite, when you find those points at the intersection of multiple subspaces, you're going to get extremely small value. So those are the points actually at the beginning you want to avoid, especially the origin. If you put origin into the polynomial, you give very small value, hopefully 0. But it doesn't give you any reliable estimation for the orientation of the normal vectors. So you shouldn't rely on p of x equal to 0 as your objective function. So instead, so this is what the lemma 3.9 tell you that what you should do is that you're going to find a projection x tilde from x onto the 0 set defined by p of x as the following. That minimizes this value. Okay? Minimize the distance. So this is approximation of the geometric distance of the projection from x, that is the observation, to x tilde, that is the projection, based on p, that's the polynomials. Okay? And the polynomials is the list of all the linearly independent vanishing polynomials from the Veronese embedding. Okay? So next we are going to prove this, this lemma. I think this is the second important result of this lecture. Can you see from over there? Or should I use this board? It's fine? Okay. So as I said, so start a proof. So we know that the optimal projection x tilde of a point x onto the 0 set of p of x must satisfy the following objective function that minimizes the Euclidean distance of the 2 points subject to p. So this capital P is equal to a list of whole bunch of small p's. That's what I use. At least after the projection, the evaluation of those coefficients at the projected point should be equal to 0, right? Which means they are on the 0 set, where L is equal to 1 to the number of what Hilbert function will tell you. Okay? So that's the condition. Okay? So immediately we have 2 results. The first result is the evaluation, as I just said. So if this is true for all the small p's, the evaluation of x tilde on capital P as a row vector has to be equal to 0, right? And second, now this is your turn. I want to ask you, what's the value for the dot product between x tilde of x tilde and the derivative of p? What's the dot product between x tilde and the derivative of p evaluated also at x tilde? I have a point x. I want to project onto x tilde such that after the projection, this guy is defined by p. Okay. And what's the derivative of p? It's orthogonal to the subspace, right? So this guy has to be equal to 0. Because after projection, this guy sits right on the algebraic, on the 0 set. So this one has to be exactly equal to 0. Okay. So next, use the Lagrange multipliers. There exists lambda, which is a vector in the dimension of the Hilbert function value that this objective function star is equivalent to star star, which is minimized with respect to now two terms. So we minimize x tilde, right? Still the Euclidean distance between the two plus p of x tilde times lambda. Okay? We call this term our objective function. Is that clear? This is a row vector, contains polynomials. This is a vector of Lagrange multipliers. Okay? So if this is good, then what's next? Can anybody tell me very quickly what I'm going to do next? After you have Lagrange multiplier function, what's next? You take the derivative, right? So you set the derivative with respect to this guy equal to 0. This is the thing that you want to optimize. So this one is equal to 2 of x tilde minus x plus the derivative of p of x tilde times lambda. Lambda is a constant. Okay? So next, so you are going to multiply this thing by the derivative of p x tilde transpose. That gives you the derivative of p transpose times the derivative of p, now as a matrix, times lambda equal to 2 of x minus x tilde. No, I have to put this one in the front because this is a matrix. X minus x tilde. So I move this guy from one side to the other side, so I have to switch the sign, right? I move this guy from one side, I have to switch the sign of the variables. And if you look at the condition I have here, so this guy multiply this guy equal to 0, right? As we set in here, because they are orthogonal to each other. So this gives me 2 of times x, right? So now, so what's the dimension of this guy? So P, what's the dimension of P? No, P is the least of all the vanishing polynomials. This one is this one, right? That's how many vanishing polynomials you have. Right? So what's the dimension for the derivative of P? Respect to D, right? So that's D times H transpose, the value of the Hilbert function. So what's the dimension of this guy? Is right? So you can see if this guy is larger than D, then this guy is guaranteed to be rank deficient. So this matrix may not be full rank. So what you can do to compute lambda is to take the pseudo inverse instead of the inverse. Remember, we can define pseudo inverse by singular value decomposition, just to remind you. Times right? So that is the first conclusion. That's the first result. The third result, actually. The fourth result is that we are going to multiply again this guy from the left by tilde minus x transpose. In that case, we get tilde x tilde minus tilde square is equal to 1 over 2. You move the 2 from one side to the other, and of x minus x tilde transpose, right? Because I moved this guy to the other side, so I have to switch side. Again, the same reason. Times the rest of this, right? P of x tilde lambda. Again, we use the conclusion, we use the result of number 2, that this one will disappear. We only have one term. So it's equal to 1 over 2 x times x transpose times the derivative of P of x tilde times lambda. Okay? And from here, we plug in lambda in here. So I suppose now you can remember these two results, right? It's very easy to remember. So I can erase it. So what do I get is that I combine 3 and 4, give me the result that the Euclidean distance of the 2 points square is equal to x transpose the derivative of P x tilde evaluated at tilde times the pseudo inverse of this matrix, of this symmetric matrix, evaluated at x tilde. Again, you have to keep track of which one are evaluated at tilde, x tilde, and which one are using x of the original observation. So this is the term. So we are almost there. You can see that now we see the roughly very similar to what we have right there, right? But we cannot evaluate this thing. Why? Because this thing contains unknowns. I have to convert that to my observation, x, right? So the first one we can approximate is that we assume that if x and x tilde are close, then at least the derivative of x tilde is equal to the derivative evaluated at x tilde is equal to the derivative evaluated at x. I assume that. Or you can take the Taylor expansion, and then you're going to the same thing. You're going to eliminate the higher order terms, the second order, third order. So this is the first order approximation. And if you put that back, so let's say equation 5 is equal to x tilde p of x now of px to x transpose px pseudo inverse times px transpose x. Okay? Now, the last thing is that what is this guy? The derivative of p evaluated at x transpose times x is equal to what is this guy? What's the value of this guy? So let me give you a simple example. Just think about that in one variable. Suppose I give you f4 of x times x, the derivative of x times x. 4 means the f is a homogeneous polynomial of degree 4. Right? Because you move for any homogeneous terms, monomials in this guy, you're going to move the fourth order into a scalar coefficient. What's left is 3, but you're going to immediately multiply by 1, and then you get back to the original polynomial. But you left with k. So that is exactly what it is there. So this is equal to k squared of no derivative p of x. I want to be correct. P of x, yeah, exactly. But you still have to compute this guy, unfortunately. Pseudo inverse times p of x transpose, right? Plus some higher order terms we have already removed. So that's it. That's the solution. Okay. So the square of this Euclidean distance is equal to k squared times this one, and the Euclidean distance itself is just k times the square root of the rest of it. Okay. So that's the result. Okay. So this actually is a very general result that I hope that in the future can also help you if you encounter any problem you want to project an observation, noisy observation onto an algebraic set. So that actually is the equation you want to use. You just go back and then look up the equation in the textbook, and then it's very simple to compute. Okay. So now if I get hold of let's see. After I project the samples onto the subspaces, I can use this objective function to find the single one that minimizes. Of all the samples, I can find one that minimizes this value, right? From there, I get one sample per subspace for the first subspace, right? But then what do you do next? Do you continue to find a second sample that minimizes this value, minimizes this objective function? The problem is that the second sample may also come from the same subspace. So the question is, next, after you evaluate that for one subspace, you have enough information to remove the entire subspace, entire point, and then the orthonormal basis, and how to proceed, how to estimate the rest k minus 1 subspaces. Any wild guess? algebraically, not numerically. What you can do is very simple. You can do polynomial division. After you get hold of this point, from the evaluation of your p, right? And for all the vanishing polynomials, you can reduce the order of the degree of polynomials by 1 by removing this component. Because you know this p is a linear combination of all those points. You remove that, what's left will be a vanishing polynomial that have the zero set of this vanishing polynomial will equal to the union of the rest of the k-1 subspaces, right? Is that clear enough? You can do that numerically. So here's the summary from top to end. So again, you start with a whole bunch of points, and then you know that based on the definition of orthogonal subspace, the normal vectors, you are going to eventually get a set of vanishing polynomials. Those vanishing polynomials corresponding to the coefficient of the null space of your embedded data matrix. And these are the polynomials. These are the coefficients. And you use that to recover P1 and P2. And then you take the derivative of P1 and P2. You evaluate the derivative of P at one sample per subspace. You get the orientation of the normal vectors perpendicular to V1 and V2. From there, you will be able to separate the samples and also recover the algebraic models for V1 and V2. This is the summary. OK? Any questions? So now let's go very quickly to cover the second situation. That is, if we know GPCA now with the known K and D, but how to proceed to solve GPCA without knowing K and D? Well, let's also consider several cases. The first case is that if we know that all the subspaces are of equal dimension, then determining K and D is still straightforward. So what are you going to do? If I tell you that subspaces are all of the same dimension, but they can be very small dimension. For example, in a 100-dimensional space, I can have all the subspaces of dimension 10. In fact, for example, for face recognition, I give you 100 by 100 resolution images. The dimension of all the pixels is 10,000, right? But you can approximate the illuminations of those faces in 20-dimensional space. So all your subspaces are 20-dimensional space. So how do you do? If the subspaces are all the same dimension, the first thing you want to do is to reduce to hyperplane case. So what you're going to do is to keep projecting those samples. If D is known, if at least you know the dimension of subspaces, you only need to use PCA to reduce to D plus 1 dimension. You need to reduce the dimension of those samples to D plus 1. And then in that case, the problem becomes hyperplane segmentation. Everything becomes well-defined, right? Everyone will be happy. So you only need to look for a single dimensional null space from the vanishing Veronese embedding. So what's the other situation? So if K is known, what we can do is that we can project samples. We just need to find the cut where all the subspace suddenly become hyperplanes. So we are going to project the samples into L-dimensional space, where L equal to 1, 2, 3. And suppose dimension D equal to 10. When you project into 1, 2, 3, all the samples are going to span the whole space. So you don't see any rank deficiency in the Veronese embedding. Okay? So once you reach the magic number of 10, you suddenly see the Veronese embedding, the matrix drop ranks by 1. So that actually is the estimation for D. Okay? Now, if both K and D are unknown, you have no choice but try all the combinations. You start with L equal to 1, and you try K equal to 2, 3, 4, 5. And then you start with L equal to 2, and then you try K equal to 2, 3, 4, 5. At least you have a certain range you want to try. For example, K cannot be blow up to 100 or 200 subspaces. If you have a range of the subspace from 2 to 5, you can try k equal to 1, 2, 3, 4, 5, and then you raise the subspace dimension to 3, 4, 5, 6. You try all the at the point where the first time the V matrix drops ranks. Okay. So how to determine the arrangement with different dimensions? Well, if the data are noise-free, you still get a free pass. In the case that, remember, we have Hilbert function. We have this table. So you can just keep raising the dimension, and then until you see the Verneza embedding drops ranks. Now, in that case, if they are not the same dimension, so you may not see the rank of V to drop by 1, the dimension of the null space. But in that case, based on the Hilbert function, you can just go to the lookup table, and then you can find the combination, right? If the null space of your Verneza embedding is 4, at least one possible solution is that the combination for the dimension of subspace will be 2, 1, 1. Okay, that's what I'm saying. Okay, so the last case, in the worst case scenario, if the data is noisy, are noisy, then you are not going to see any sharp indication for the number of the dimension of the null space. So in that case, you still go back to the drawing board for hyperplane segmentation. So you're going to do that iteratively. For example, if you have this situation, you have noise in the data space, and what you can do is that, so this is based on the so-called effective dimension. You can look at this definition in chapter 3.5. It's a very simple definition, but basically what it does is that you start with this whole bunch of points. You know, what's the most stable procedure you do for segmentation? We all know, we all want to do all the time, segmenting hyperplanes, right? So regardless how many subspaces you have, you're going to try segmenting k subspaces. So you just assume that you have k subspace with known d but unknown k, right? In this case, you raise the assumption for k equal to 2. There you see a rank, the rank of the Verneza, the data matrix drops rank. In that case, you are going to use hyperplane segmentation to partition this data set into 2 subgroups. Okay? And now, if you continue to do this, you want to partition this group into a hyperplane. In this case, in 2-dimensional space, the hyperplanes are lines. But within a certain range, k equal to 1, 2, 3, 4, 5, no matter how you increase k, as long as you don't increase to 100 or 1,000, you're going to see that the Verneza the data matrix is still full rank, because you have a whole bunch of points spent on the 2-dimensional plane. No matter how you find them, you are going to still don't satisfy the rank deficiency. Okay, so you are going to put that right there, keep it there, because you don't see any within certain reasonable range. But this guy, if you raise the k assumption for the hyperplane to 1, 2, 3, 4, at 3, you can see that you can further partition that as a hyperplane segmentation in R2. You find 3 planes. You find 3 lines. Okay. So as the procedure continues, the effective dimension will continue to drop from 3 to 2 point something to 1.6. But what I'm saying is that if you continue to segment these things to some finer structures, you are going to see this effective dimension, in fact, go up. So this one actually reaches a local minimum value for the effective dimension. And this so-called iterative GPCA will stop when you try to attempt the next segmentation of hyperplanes, but in fact, the effective dimension will go up. So the algorithm will stop. Okay? So that concludes the section 3 GPCA. Okay? Thank you very much.